So we're asked to find the expectation value of the z component of our angular momentum of our wave function, which is A varying with r and theta times by cos phi. And our expectation value is denoted as L, which is angular momentum, the z component, is 2 pointy brackets. I'm going to start off by defining what the expectation value actually is. So in the classic world, you can measure how fast the top is spinning and you get one definite answer. But in the quantum world, particles only exist in probabilities, so you can't exactly predict where one is going to be. The expectation value is just a statistical average of, let's say you have thousands of particles, all in the same wave state as R1 right here. You measure the angular momentum of each one, and you take that average, you get the expectation value. So, we're given in a hint that Lz is equal to triple bracket psi complex conjugate Lz d cube r all over this is just shorthand for all observable space. Complex conjugate, or in bracket notation is just a complex conjugate, z component of angular momentum operator, all over our normalization, which is just equal to 1 because it's a probability. Okay, so first we know that the operator Lz hat is equal to minus I h bar partial of d by d phi. So when we applied it to this, we are going to get Lz hat psi is going to equal minus I h bar phi a r only one thing in here varies with phi, which is cos. So we're going to minus sign, it's going to cancel that minus. So we're going to get I h bar a r theta sine phi. Okay, and the complex conjugate is just going to be equal to a star r theta, because this doesn't have an imaginary part. I'm just assuming this constant does. So we put into here, we're gonna just remove, we're not gonna think about these parts, this is just a normalization, it's just equal to 1. We're gonna get recall that for a wave function, when it's multiplied by its complex conjugate, you just get the probability density. So we can put that here, a r theta squared sine phi cos phi, and because we're using spherical coordinates, r squared sine theta dr d theta d phi, and our limits are infinity and 0 for dr, pi and 0 d theta, and 2 pi and 0. Oh, and let me not forget, let's not forget IH, which is going to go on the outside here, IH bar. So the expectation value is this. Now this looks like a mess right now, but you can already see that if we just take out the integral of phi, which is sine theta, sine phi, sorry. If you know your integrals, this is just half sine squared, yep, 2 pi 0, which is 0, which means this whole expression equals 0. The expected angular momentum of the z component of this wave function is just 0.